So we're going to be talking about how to implement insertion sort. Well, as a matter of fact, as we mentioned earlier, one of the benefits of insertion sort is it's very simple to write. So if you are so inclined and you really want to learn the algorithm well and you want to improve your coding skill, pause the video and try to write insertion sort yourself, given you know how it works. Okay, so whether you've done it or not, I'm going to show you the code, which I already typed out here. And I'm going to go through it line by line. So first of all, as with any sorting algorithm, it's going to be a loop. Now, we are going to loop through kind of the unsorted portion of the input iterable. And so the very first index at which the unsorted portion starts is at 1, right? Because remember, if there's a single element, the single element at 0, it's sorted, right? So we start at 1, and unsorted index is kind of the first index of the unsorted section, okay? And once we get inside the loop, the first thing we do is we remember what the element at that unsorted index is. And then we'll have another index, k, that kind of travels inside the sorted portion and try to find the right place to place the unsorted data. Okay, so that's what k is for. So, and as I said, so k kind of travels towards the beginning, and that's why we do k minus equal to 1 here. We decrement it by 1 each time. And how long do we stay in the loop here? Well, as long as k is not yet at the beginning of the list, and as long as the k minus 1 element is bigger than the data we're trying to insert into the sorted portion, right? So we keep traveling, and in the process of traveling, so if the data we're looking at the index k minus 1 is greater than the one that we're trying to insert, then we pull that data kind of forward 1, so that we create a little gap or a hole that we can insert our unsorted data. And then we just repeat the process until we get out of it. And when we get out of it, what the k is going to hold the position that we're going to put our unsorted, the first piece of unsorted data into. And that's when we do the assignment. Now, as with any of these algorithms, with any algorithm that actually loops in looking at indexes, make absolutely certain that you understand why it's a -1 here, right? And why this is k rather than k minus 1. So the only way for you to really understand it is to kind of trace through the code with an actual list. So if you don't immediately see, well, why we do a -1 here and we don't do a -1 there, or any of those things, please do trace through the code with the list and with a pen and on paper, or you can trace through the debugger, either way. Okay. All right, so that's really how this piece of code works. It's mostly simple, as long as you get the index correct. One question for you is, we said that insertion sort, any sort of sorting function should work for empty list or list with single elements. So does this loop work for that? So and I hope once you think through it, it should be fairly obvious. All right, and once we write the function itself, we really are the test. And since we've already set this up earlier, it's very simple to apply a set of tests to the insertion sort. And I've already written that up here. It's very, very simple, just like in the bubble sort case. And we can run it. And yeah, like I said, insertion sort is also n squared, so it's going to take a while. I'm not going to complete the run here. Just want to mention the performance. Here is the performance number from one of my runs. And here I have a comparison of insertion sort with bubble sort, and I plot them out. Now, if you look at these numbers, it's quite interesting. Insertion sort, for every single size is about twice as fast as bubble sort, or half the time, right? Even though they have the same big O, but insertion sort is faster. And the intuition behind that is, bubble sort. Remember the way it works, it always bubbles the largest to the very end of the list. Whereas insertion sort, on average, it doesn't have to insert it all the way at the beginning, right? That's the worst case. On average, it should be able to find the right place, kind of in the middle of the sorted portion. And I think that is the reason why the insertion sort is usually twice as fast as the bubble sort.